because the Thursday class meets before the Tuesday class. Well, it's not too much trouble to post them both, but we'll see how it works out. It'll pan out. Okay. Yes, if you have the homework that's due today, go ahead and just turn it into this pile right here. And then take a seat and we'll get started. So I apologize if it's stuffy in here, but I got no control over the thermostat. All right, so we left off last week. I think we finished up talking about IQR as a measure of spread. Okay, and we talked about finding the quartiles Q3 and Q1 and Q3. And we also talked about measures of center. All right, and we had the median, okay, which is technically the second quartile. The median is the point at which half the numbers are larger than the median and half the numbers are smaller than the median. Okay, and then we also talked briefly about the mean. Okay, and the mean is the point, the balancing point. I think I covered the mean as the balancing point. Did I? So if we had some distribution of data points like so, the median is the point at which half the numbers are larger than this number and half the numbers are smaller than this number. So perhaps somewhere right there, that might be the median. And the mean is the balancing point at which the entire thing rests. So here I've kind of illustrated the median, and here I've got the mean. Okay, and so this is just a few, I guess, things to cover. Is that the mean? The way we calculate the mean, which is a measure of center, basically telling us where the middle of our data lies. We add up all of the points, the sum symbol of y. So we add up all of the different points. That's this summation of y, adding them up, and we divide by how many points we have. So n is the number of points we have, and that's our mean. I believe this was all covered last week, correct? Okay. If I think I covered something last week but I didn't, please say this is something new that we haven't seen before. Okay. All right. So when we're talking about this, there's a few things to keep in mind regarding the median and the mean. Okay. Both of these tell us where the center is. Okay. However, for skewed distributions, the median and the mean will be a little bit different. Okay. For symmetric distributions, the median and the mean will be about the same. So these are good points to remember. So symmetric distributions okay, the mean will be approximately equal to the median. Okay, and I should say approximately. The mean and the median are approximately equal. And again, symmetric is anything where you can kind of draw a line down it and have a mirror image on one side as the other. Things get bigger on this side, and then things are also getting bigger. So it could be like this V shape or this mountaintop, a bell curve, whatever you want to talk about. Those are symmetric distributions, okay? And then, so for skewed ones, we have skewed right, And then we also have skewed left. Okay, so is this skewed right or is this skewed left?
Right.
This is skewed right because we would stab you with the right-hand side. Okay, so skewed right, on skewed right, the mean is larger than or greater than the median. Okay, and so again, I kind of drew this line to show where the median is, and here we have the mean over here. And so the mean is to the right of the median, meaning that the mean is larger than the median. Okay, and just the converse applies for distributions that are skewed left. So if it's okay, I'm going to go ahead and erase this little diagram and say for distributions skewed left, the median is larger than the mean, or the mean is less than the median. Okay, for distributions that are skewed left. Okay. All right, so those are our measures of center. Okay. And then we talked about the interquartile range, the IQR, as a measure of spread. And then we also briefly touched on the range as a measure of spread. So IQR is the distance between the third quartile and the first quartile, Q3 minus Q1. And then we have the range, also a measure of spread. Okay, so these are all measures of spread. And then the last measure of spread that we didn't really talk about is the standard deviation. Okay. The standard deviation is one of those terms that you hear thrown around very frequently in statistics, but at first nobody really knows what the standard deviation is or what it even means, and in the beginning it doesn't make a whole lot of sense, and I'm going to give you the definition and tell you how to calculate it. But at first it might not make sense, but I'm hoping that as you guys deal with the standard deviation and work with it a little bit, it'll become a little bit more familiar, like your miles per gallon. As a kid, you never cared what miles per gallon were, but as you started driving and filling up your tank, then you started appreciating what these numbers mean. Okay, so the standard deviation, a rough definition, okay, is I'm going to just write this down, and it might not help anything, but we will see. Okay. So a rough definition is the square root of the, quote, average squared distance from the mean. So I'm going to push this up and let you guys write that down. Okay, so it's the square root of the average squared distance from the mean. So what does this even mean? Okay, what are we talking about here? So let me see if I can find a few points. Okay, so let's say we wanted to calculate the standard deviation of a certain set of numbers here, okay? So let's say our set of numbers, we have 4, 3, 10, 12, 8, 9, and 3. 4, 3, 10, 12, 8, 9, and 3. And then let me also just make a number line here. To illustrate. So we will start off with, this will be 0, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I tried to draw these breaks as evenly as possible. But so we've got a data point at 3, 1, 2, 3. I'm sorry, a data point at 4, a data point at 3, a point at 10, we have a point at 12, we also have a point at 8, a point at 9, and another point at 3. Okay, so we've got these dots, and let me just, okay, so if we wanted to calculate the mean, just imagine all of these circles representing equally sized masses, and this is now like a seesaw and a teeter-totter. You know, where do we want to place the balance? Okay, that is going to be where our mean is. So, so our mean, we would add up all of these numbers. So we would add up 4 plus 3 is 7, plus 10 is 17, plus 12 is 29, plus 8 is 37, plus 9 is 46, plus 3 is 49. Okay, so the mean is 49 divided by the number of numbers that we have. We've got 7 numbers. So this conveniently comes out to 7, okay? And so this says if we were to make a teeter-totter balance, we would place the balance right here at 7, and this is the mean. Okay. So this definition, the standard deviation, as the square root of the average squared distance from the mean. So remember, we're going to get into the calculation of how to calculate the standard deviation and things like that. But I don't want you to get lost in the formula, okay? It's important to know the formula and know all the steps and parts of the formula. That's true. But the overall concept is that standard deviation is a measure of spread, okay? And a measure of spread tells you how far out the numbers are spaced or how close together they're clumped, okay? Just like with the IQR, with a large IQR, that meant your numbers are very far spaced out. And with a small IQR, they're clumped together, okay? And so here, we're going to talk about, we've got the mean right here, and we want to know the distance from the mean. So it looks like these points over here are very close to the mean, and then out here we've got some points that are far away from the mean, and these points are kind of far, maybe not too far, or whatever. And so it's kind of the idea of the average distance from the mean, okay? But it's not the average distance, it's the quote average squared distance from the mean. So if it was the true distance from the mean, over here we'd have positive distance, and on this side it's technically like a negative distance because they're smaller than that. So what we're doing is we're going to square everything. So everything, when you square it, becomes positive. And so we're looking at the squared distance from the mean. And then we're going to take the quote average. It's not the true average, but the quote average. And we won't get into the reasons for that. And then once we take the average of that, then we take the square root of that, okay? So I will lay out all of these steps that go into the calculation here. But again, the overall concept is that the standard deviation is a measure of spread. When you have a large standard deviation, it means your numbers are more spaced out, more spread out from the mean. With the smallest standard deviation, it means your numbers are closer to the mean. That's the important concept. That's the big picture concept that I want you to make sure you understand. So standard deviation, measure of spread. That's the big picture concept. And so here, let's go into the steps. So the first step, step 1, is calculate the mean. Okay, and we've already done this. We added up all of these points, and we got the mean is equal to 7. Okay. Step 2. We subtract the mean from each number. Okay? So here we've got these 7 numbers, 4, 3, 10, 12, 8, 9, 3. And we're going to subtract the mean from each of these numbers. Okay? So I'm going to do 4 minus 7. I'm going to do 3 minus 7, 10 minus 7, so on and so forth. Okay? And so what I'm going to write here is I'm going to write difference from mean. Okay? And these are going to be, I'm going to just do 4 minus 7. And so 4 minus 7, we get negative 3. 3 minus 7 is negative 4. 10 minus 7 is 3. 12 minus 7 is 5. 8 minus 7 is 1. 9 minus 7 is 2. And 3 minus 7 is negative 4. Okay? So that's the second step. We subtract the mean from each of these numbers. Okay? The third step is we square all of the differences. Okay, so I'm going to square each of these numbers here. Okay, so I do negative 3 squared, negative 4 squared, 3 squared, 5 squared, 1 squared, 2 squared, and negative 4 squared. Okay? So that's going to be step 3. And so the resulting numbers that we get, I'm going to write them down here. We have 9. We have 16. 3 squared is also 9. 5 squared is 25. 1 squared is 1. 2 squared is 4. And 4 squared is 16. Okay? Have I lost anyone at this point? Or are we all following? Okay. So once we square all of the differences, the fourth step is we add up these numbers. Okay, so we add up these numbers and we do 9 plus 16 is 25. 25 plus 9 is 34. 34 plus 25 is 59. Plus 1 is 60. Plus 4 is 64. Plus 16 is 80. And let me just double check my math. And yes, when we add up these numbers, that gives us a total of 80. Okay, so we add these numbers up, and that gives us 80. Okay. Step 5. All right, and that's okay? No questions on where I got 80? Yes?
Actually, back to the subtracting the mean from each number, 7 from each of those.
Yeah, so all of these are the original numbers that we had, and I subtracted 7 from each of these. So I got 4 minus 7 is negative 3. 3 minus 7 is negative 4, correct. And I did that to all of them. Okay, step 5 is we divide by n minus 1, okay? So when we find the average, we normally add them up and we divide by n, okay? In this case, we're finding something kind of like the average, but it's not quite the average. We add up the numbers, and instead of dividing by n, we're dividing by n minus 1, okay? And the reason for this is very technical. It has to do with this concept of degrees of freedom. It's beyond the scope of the course. We don't need to worry about why we're choosing n minus 1. Just know that we're dividing by n minus 1, okay? And so here, that becomes 80 divided by n minus 1. We have 7 numbers. Our n is 7, okay? So again, n is the number of numbers, okay, which is 7. So 7 minus 1 is 6. We do 80 divided by 6. Okay? And that gives us 13.33. Okay? It's just a coincidence that our n is equal to our mean. Okay? So don't think that this n came from the mean, but the n is the number of numbers that we have. Okay? This was just a coincidence. Okay? And finally, the last step Step 6 is take the square root. Okay, so we take the square root of 13.33, and we get our standard deviation, and that is equal to 3.65. Okay, the standard deviation is always positive. Always positive. Okay, and again, if we compare this, the square root of the average squared distance from the mean. So in step 1, we found the mean. In step 2, we subtracted the mean from each of these. So that's kind of the distance from the mean. And then step 3, we squared it. So we've got the squared distance from the mean. And step 4 and step 5, we add them up and we divide by n minus 1, which is almost like taking the average. And that's why I have average in quotes, okay? We're not dividing by n. If we divided by n, that would be the true average, okay? But we're dividing by n minus 1, so it's the quote average, okay? So that's why it's the quote average squared distance from the mean. And finally, in the last step, we took the square root of that. And that's why we have the square root of the quote average squared distance from the mean, okay? Are all of these steps in finding the standard deviation okay? Are there any questions on any of these? All right, so each of these steps, when it's broken down, is not too difficult, right? It's just, you just have to know each of these steps that you do, okay? I'm going to write the formula for the standard deviation, okay, which at first is going to appear a little bit scary, but if you break down the formula into the different steps that we've done, it's not any scarier than these 6 steps, okay? So the formulas, all it is just, I guess when you get comfortable with formulas, it combines all 6 steps into just one handy little equation / formula. But of course, you know, the first time you see it, it is a little bit intimidating, so. All right, so the standard deviation, which is given by the symbol s, all right? Sometimes it's given by the Greek symbol sigma, and we won't worry about that yet, okay? The formula for the standard deviation is okay, so this is the formula for the standard deviation, okay? And you know what? I forgot that this is already up. So I'm just going to rewrite this formula in a more open space where I can just draw arrows all over it, okay? But don't worry, it's if you wrote it down on your paper, that's fine. But okay, so it's the square root of the sum y minus y bar quantity squared divided by n minus 1. Okay, so if you had no exposure to statistics and we just threw this formula at you, it might be a little overwhelming, okay? But it's not, all right? Step 1 was calculating the mean, okay? That's given by this symbol, y bar. This is step 1. Okay, so you calculate the mean and you have y bar. Okay? Step 2 is subtracting the mean from each number, okay? And that is this part, y minus y bar. So basically the minus sign is step 2. Just subtract y bar from each y. All right? Step 3 is we square all of those differences. So that's this number 2 squared. That's step 3. Once we find the difference, y minus y bar, that's the difference, we square it, the third step. So it's not too difficult. The fourth step is we add up all of these numbers. Okay, and that's again given by the Greek symbol sigma, for the capital sigma for adding up, meaning summation. Okay. Step 5 is divide by n minus 1, and that's given by n minus 1 right here. That's step 5. And finally, the last step is take the square root, and that's by this radical sign, step 6. Okay? So all 6 steps are just given in one equation, one formula. But again, broken down, the concept behind standard deviation, or the steps behind calculating the standard deviation, is not too difficult. Okay? Each of these steps are just arithmetic that you've got to do. Okay? And again, the overall concept of the standard deviation is the square root of the average square distance of the mean. Okay, that's, or maybe not the overall concept, that's kind of the word definition. But the big picture concept is that the standard deviation is a measure of spread. For numbers that are spread far apart, the standard deviation will be large, and for numbers that are small, the standard deviation not numbers that are small, but numbers that are close together, the standard deviation will be small. Okay? So we look at this number 3.65, and we've got this, the mean is at 7. So 3.65 kind of goes from here to about, right about here. So this is covered by one standard deviation. And over here, if we go out 3.65 in this direction, that takes us out 7 plus 3.65 takes us almost to 11, okay? And that's one standard deviation, okay? So here we go out one standard deviation each direction, and we've covered quite a good range of points, but we've left out a few points over here, and we've left out a few points over here, okay? And so, maybe this is not the best illustration. We've only got a few points to talk about how big the standard deviation compares. But here we've got the idea that the standard deviation, once we start going out this distance from the mean, we start encountering data within our points here. Okay? Okay. All right, a few last points from Chapter 4. So we're just wrapping up Chapter 4 right here. And all of Chapter 4 was how do you describe a distribution? Okay, and so if it's okay, I'm going to go ahead and start erasing this stuff. It's actually getting kind of warm inside here, so I'm going to just remove my coat. Yes? I'm sorry, what page? What page in the book? I don't know, I was just wrapping up Chapter 4, so that's, I guess, 74. That's just got this formula for the standard deviation. Something around there, 66, 64, something around there. It's not so critical, okay? But just let me just wrap up with when describing a distribution. Okay, things you want to talk about. Yeah, I guess 66. I don't know. Page 66. All right. When describing a distribution, include. All right. Talk about the shape of the distribution, the center of the distribution, and the spread. So these are the three things we want to talk about. So shape, we talked about the idea of being symmetric or skewed, unimodal or having multiple peaks, multimodal. Okay. Center, we've talked about the median and the mean. And spread, we've talked about the range, the IQR, and just now the standard deviation. Okay. So maybe I'll throw these terms up there. We've got unimodal, multimodal, symmetric or skew. We have the mean and the median. And we also have the standard deviation, IQR, and range. Okay. All right, so all of these things are good. And let me just say just a few points and just say for symmetric distributions, we prefer, and it's not a law, not a rule, okay? But in general, we prefer the mean and standard deviation as for measures of center and spread. And for skewed distributions, we prefer the median and IQR. And these are not, again, not rules, but these are general preferences that we have about which numbers to use. Okay. So that wraps up Chapter 4. Now let's get on with Chapter 5. Okay. All right, so in Chapter 5, it introduces what they call the 5-number summary, which is just a fancy term for basically the range and the IQR, but, well, not quite, but let me just talk about the 5-number summary. Okay, the 5-number summary is basically a summary of quantitative distributions. So this starts off with the minimum, the first quartile, the median, the third quartile, and the maximum. Okay? And that's simple enough. Okay? Those are your 5 numbers that compose a 5-number summary. All right? And from this, you can immediately find the range. You just do the max minus the minimum. And you can also find the IQR just as easily. You do Q3 minus Q1. And so from there you've got an idea of your spread and things like that. Okay? Another tool that we use, okay, is a graphic tool. Called the box plot. Okay? So graphic tool, and that's the box plot. Okay. Now I wish I could tell you the box plot was just the 5-number summary in graphic form, okay? Which many times it is, but there's a few extras that we include on the box plot that we don't include in the 5-number summary, okay? But the core of the box plot is also the core of the 5-number summary. So the core of the box plot is going to be these 3 numbers, Q1, the median, and Q3, okay? So your typical box plot is a box or a rectangle with some line down the middle, and then a whisker coming out this way, and then a whisker going out the other way, okay? Sometimes it's vertical rather than horizontal, okay? Sometimes you'll see it like this, all right? But they're both box plots, okay? All right, so the core of the box plot will be true. So let me just talk about the center, the box, okay? And this line in the middle of the box, that's the median. Okay? The left edge of the box, that's the first quartile. And the right edge of the box is the third quartile. Looking for, here we are. Okay? And then we have the whiskers, which extend out to the left and to the right, okay? And I don't want to say they're the minimum and the maximum just yet, okay? A lot of times they are, but sometimes they're not, okay? And so I'll get into the explanation behind those, but let me just say the left edge, okay, is going to be the smallest point within the fence, and over here we have the right edge over here is the largest point within the fence. Okay, and I haven't talked about what the fence is, so we will get into that. But let me just throw this out there. The smallest point within the fence, sometimes the smallest point within the fence is the minimum. And over on that side we have the largest point within the fence. Sometimes the largest point within the fence is the maximum. Sometimes it's not. Okay, so let's use a data set and create a box plot. All right. So last week during lecture, I used a data set of pulse rates, and let me go ahead and just and write all of these pulse rates down again. So just forgive me. We had 56, 60, 64, 64. We had the number 64 3 times, the number 68 4 times, the number 72 4 times, the number 76 4 times, the number 80 4 times, the number 84 twice, and then the number 88 once, okay? And you have to break up your all of your numbers over 2 lines. That's fine, or 3 lines, however many lines it takes. It doesn't matter, okay? And last week we found the median and the quartiles for this, remember? Okay, so how do we find the median? We counted up the data points, and we've got 24 of them, I believe. Let me just count. 1, 2, 3, 4, 5, 6. Yes, we have 24. Okay, so we have n equals to 24. So the median would be, the position of the median is n plus 1 divided by 2. So that's 24 plus 1, or 25 divided by 2, 12 and a half. Okay, and so we find the 12 and a half number in our list. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is the 13th number. So the number in between the 12th and the 13th is going to be in between 72 and 72. So our median is 72. Okay. And then once we divided our list into 2 separate lists, the smaller list and the larger list, we found the median of each of those lists to find our quartiles. Okay. I'm hoping this is familiar. All right, so on this side we have 12, and so the median, the quote median of this smaller list of 12 is going to be in between the 6th and 7th number. So we go 1, 2, 3, 4, 5, 6. The 6th and 7th number are both 68, so the first quartile, Q1, is equal to 68. And on this side, we take the median of this number, these sets, and we go 1, 2, 3, 4, 5, 6. The number in between the 6th and the 7th number is going to be 80. Q3 is equal to 80. Okay, and we have 1, 2, 3, 4, 5, 6. So as the name quartile would suggest, we've divided our list of 24 into 4 quarters, each quarter being the same size. And we've got 6 in this quarter, 6 in this quarter, 6 in this quarter, and 6 in that quarter. Okay, so as we would expect from a quartile. All right, and we also have the minimum and we also have the maximum. Okay, and so we have our three center numbers for in order to create our box plot. Okay, did I lose anybody in finding Q1, Q3, or the median here? We're good. Okay, good. All right, so let me just, I'm going to create a scale, a number line. So when you guys make a box plot, please don't just draw a box and say this is 68, 72, and 80, okay? This kind of bothers me because the distance between 68 and 72 is only 4 units, and this is much bigger than the distance between 72 and 80, okay? And that's not how they work, okay? You have to, everything is in context, and so you have to kind of have a scale to begin with. And so I'm going to just start off by labeling this 50. We'll go out to here for 60. We'll go out to here, I'm hoping approximately the same distance, all right, to 70, and then out here, I don't know. It's kind of hard when you're up at the board. So this is 80, and if we go out to 90, it would be somewhere about here, okay? So this is the best I could do in terms of, and then so this would be 55, 65, 75, and 85, okay? So it doesn't have to be exact, but this is at least an approximate spacing of equal spacing here, okay? So we can create the core of our box, 68, 72, and 80. Those are the, that's Q1, median, and Q3, okay? So I'm going to start off with 72, and I'm going to draw a vertical line at where about 72 is, okay? Then I go out to Q3 for 80. And then I go down here to 68 for Q1. Okay, and then I connect this, and we have our box here. Okay, so that's the center of our box. 68, 72, and 80. All right, and we can say 68, 72, and 80 here. All right, and that's fine. And the distance spacing there is approximately correct there. All right. Okay, and so now we have to figure out what the smallest point within the fence is and the largest point within the fence is. Okay, and again, I haven't talked about fences until now, so I will tell you what the fences are. Okay, the fences. So once we have our box, the width of the box is essentially the IQR, right? The IQR is Q3 minus Q1. So the width of the box is the IQR, okay? What the fence is we go out we go out 1.5 times the IQR in this direction, starting from right here. And then we also go out from this edge of the box, we also go out 1.5 times the IQR. Okay, so we go out 1.5 times the IQR in this direction from the left edge of the box. And then over here we go out 1.5 times the IQR in the right direction. Okay, and wherever that ends, that becomes our fence. So wherever they end, they fall, that becomes our fence. So let me write it down in terms of like equations or formulas. So the right fence, the fence on this side, this is known as the upper fence because it's the larger one. So the upper fence, that is given by Q3, the third quartile, plus 1.5 times the IQR. Okay, and the fence on this side, this is known as the lower fence. Okay, that's given by Q1 minus 1.5 times the IQR. Okay, so let's go ahead and calculate what the lower fence and what the upper fence are for our data set. Okay, so our IQR here is going to be Q3 minus Q1. So our IQR is 80 minus 68. We have an IQR of 12. Okay, that's okay with everyone? All right, so our lower fence is Q1 minus 1.5 times the IQR. So Q1 is 68 minus 1.5 times the IQR. So we have 1.5 times 12. And if you do 1.5 times 12, you get 18. So 68 minus 18 is equal to 50. And so our lower fence is at 50. This is our lower fence. Lower fence is at 50. Okay, so that's 1.5 IQR in this direction. Takes us that way. All right. Over here, for the upper fence, we do 80, which is Q3, plus 1.5 times our IQR. So 1.5 times 12. So we get 80 plus 18. That turns out to be 98. Okay, so I just have to extend this out another 10 units. And so 98, this becomes our upper fence at 98. So now that we know our fences, we can go back and look at what is the smallest point within the fence and what is the largest point within the fence. So here, the smallest point that we have is 56. 56 is inside the fence. It's going to be right here. Oops. So the left whisker extends out to 56, which is the smallest point within the fence. On this side, our largest point that we have is 88. 88 is inside the fence. It's over here. And so the largest point within the fence is over there. And so we have our box plot for this data set. Okay. Are there any questions on any of the steps that I did for finding anything? Yes?
Do you have to label them? Like
lower fence and upper fence?
yeah, and
Oh, label these 68, 72?
yeah.
Not always, okay? I mean, if it's wide, spaced out, no, okay? If it's not clear what these things are, if you don't have another separate thing that says Q1 is this and median is this and Q3, it's a good idea too, okay? But I'm not going to nitpick over your things if it's very clear where your boundaries are, okay? Okay, so what happens if the smallest point is outside the fence, all right? And we haven't talked about this, but
We pick another point that's within the fence.
yeah, so let me explain what happens here. Okay, so let's say within our data set, okay, we have I don't know, like this. I guess these are pulse rates of women, but let's say we had someone like Lance Armstrong, but the female version, okay, and she has a pulse rate of like 34, okay, or something ridiculously low, all right? Okay, so 34, I don't know if you guys can see, but changing 56 down to 34 does not change our quartiles, right? The medians, the quartiles, those are all based on the position. So it doesn't matter that I've changed some numbers here. As long as we've got 24 numbers here and we're not shifting the other numbers around, our quartiles and our median will stay the same. So in other words, our the center box stays the same, our IQR stays the same, and because the center box and the IQR stays the same, the location of the fences also stay the same, okay? However, our smallest point within the fence is no longer 56, but the smallest point within the fence is now 60. So what happens is the whisker ends at 60, and this point 34, which is way out over here, is represented with a star. Okay, so any point that is not within the fence gets represented with a star. Okay, so I should say points outside of the fence are represented by stars or sometimes circles, okay, or dots. Okay, stars or dots. So we don't actually draw the lines out to them, but we draw stars to where they're located. Yes.
Is it just one symbol for any amount of points outside of the fence, or is
No.
it one symbol per point?
Per point. So I can actually illustrate that right here. So let's say we had, female version of Lance Armstrong and her also highly athletic, but not quite so athletic cousin. Okay, so we have their pulse rates are 34 and 48. Okay, again, the quartiles don't change, our fence locations don't change. However, the smallest point within the fence is now 64. Okay. And I've run out of board space, but over here, I would draw a star for 48, and then you just imagine that this is wide enough to represent what needs to be represented, and this we've got another star at 34. So each point outside of the fence gets represented with a star or dot. Yes, you have a question?
If you have two 34s, you just put one on top of
Yeah, if you've got two of them, you just put one on top of each other. And that's fine. And you lose a little bit of like, oh, there's actually two, or I mean, and this is all just very technical. It's not, these are not rules about graphs and things. Sometimes they'll draw a dot and then put another circle around it to make sure you know that there's 2 points there and things like that. But yeah, don't sweat it. These are very on top of each other is fine. Okay. And again, if I were to change some numbers over here, we go out to, I don't know, 100, okay? Again, our quartiles haven't changed. The location of the fences haven't changed. But now, the largest point within the fence is 84. So our box goes out to here, and then the lady with the hummingbird heart has a pulse of 100, and she's represented with a star. Okay, and that's.
She must have liked the doctor, right?
Yeah. So, yeah, for whatever reason, okay, they have high pulse rates or low pulse rates. This is how we make box plots here. Okay. Questions on box plots? All of these things. Okay. So the term that we use for these points that are represented with stars, these are known as outliers, okay? So anything that's outside the fence, these are known as outliers. Okay? Extraordinary points, points that don't fit in with the rest of the data. Okay? They're known as outliers. So all of these guys would be considered outliers, okay? All right, so when you encounter outliers, there's often two temptations. One is just to say, well, they're there, and we will just continue with our analysis as if nothing is unusual, okay? Don't do that. And the other temptation is, oh, these outliers are inconvenient, let's throw them away, okay? Don't do that either, all right? Data is always significant, so the outliers could be, they could be mistakes, like somebody is recording everybody's weight in pounds, and then somebody records their weight in kilograms, okay? That person is going to look very, very much lighter than everyone else, okay? Like their weight is much smaller than everyone else, and would probably show up as an outlier. Don't just continue your analysis and just say, oh, we had one person that was very lightweight. Look into it, and if it's very clear that it's a mistake, then correct the mistake and go on with your analysis, okay? Or if there's something unusual happening, and it makes sense to not include this point in your analysis, then yes, you can remove the point from your analysis. So let's say, I don't know, let's say you were measuring people's heights, and then one of your person was an NBA basketball player, okay? And so they're an outlier in terms of height, okay? And you wanted to get just some information on typical heights, okay? And you can say, all right, well, this NBA basketball player should not be included in our survey of people for typical heights, so we're not going to include him. If that's your justification, that's fine, okay? But you could say, well, you know, NBA players are people too, and maybe we should include them in our analysis. And so, you know, there's some judgment calls there, but there should always be a reason for why you either left an outlier in or why you threw an outlier out, okay? Don't just throw away data for no reason, or don't. But if something is unusual, don't just leave it in there and hope that it's not going to mess up your analysis. Okay. So we've talked about making box plots. Can we talk about comparing them? So let me try to draw this. So we drew a box plot horizontally, but let me draw one or a pair of them vertically. Okay. So here, let me just draw this. Okay, so this is going to be a box plot on roller coaster speeds. And I'm going to have two box plots. One is for steel roller coasters, and the other is for wooden roller coasters. Okay, so for steel, it looks like okay, so these are our box plots for steel and wooden roller coasters. Okay. What can we say about steel and wooden roller coasters? Comparing the speeds of roller coasters here.
Steel's faster.
Steel is faster, okay. All right, and what makes you say steel roller coasters are faster than wooden roller coasters? Because I can say, according to our box plot, we have data down here where we've got a 40-mile-per-hour steel roller coaster, and we've got an 80-mile-per-hour wooden roller coaster. So can we say something a little bit more than just steel is faster than wooden?
The range is higher.
The range is higher, okay. So that just means, we've got some steel roller coasters that the top speed of the steel roller coaster is definitely higher than the top speed of the wooden roller coaster. But the range just talks about the spread, okay? Average speed. Okay, so we're talking about the medians. So here, okay, so overall, the general idea is correct. Steel is faster than wooden roller coasters, okay?
The distribution of the wooden seems to be more symmetrical than the steel one.
Maybe, I mean, this...
Q3 and Q1.
Yeah, I hesitate to start making conclusions about that just yet. But, okay, so the big picture idea is that steel is faster than wooden roller coasters. That's true, okay? But specific things we can say is, the median speed of the steel roller coasters, okay? Okay, is higher than the median speed of wooden roller coasters. That's clear, okay? So this median line is higher than that median line, okay? Of wooden roller coasters. But even more impressive is that the median speed of the steel roller coasters, so this means the point at which we have half the roller coasters faster, half the steel roller coasters faster than this point, and half the steel roller coasters slower than this point. This looks to be about equally or even higher than the third quartile of the wooden roller coaster, okay? So the median of steel seems to be about equal to Q3 of wooden, okay? which means half of the steel roller coasters are faster than over 75% of wooden roller coasters. Does that make sense? So this is the point that separates the top 25% of wooden roller coasters from the other 3/4 of wooden roller coasters. And here we've got the halfway point of the steel roller coasters essentially beating that, okay? And over here we've got Q3 of steel almost equal to the max speed of wooden, okay? I don't know if you guys can see that with here. This is Q3, remember? So Q3 is almost the max speed of wooden. So Q3 of steel is about equal to the max speed of the wooden, okay? Meaning the top 25% of steel roller coasters is faster than any wooden roller coaster on the planet right now, okay? And we even have this outlier at 120 miles per hour, okay? Which seems a little crazy, okay? If you go skydiving, and you're diving, like a bullet down towards Earth, okay, your terminal velocity is about 120 miles per hour, okay? That's just because of your own, at that point, the friction that your body creates between the air slows you down to 120 miles per hour. So here's a roller coaster that somehow gets you to 120 miles per hour, and so that's like, oh, is that even possible? And what if you were to look up this roller coaster that reaches this max speed? It's because they've got some sort of some system that actually shoots you out at 120 miles per hour. So it's not just gravity based, okay? You're not just going down a really steep slide, okay? But there's actually something that accelerates you to 120 miles per hour, because apparently 100 miles per hour is not thrilling enough. So they have to throw you at 120, okay? Yeah, and there you have it. But yes, we can make comparisons, but this also shows us that the slowest steel roller coasters, okay, of about 40 miles per hour is equal to about the slowest of the wooden roller coasters of about 40 miles per hour. So if you go to Six Flags Magic Mountain, you have Gold Rusher, okay, which is like their slow roller coaster, but it's a steel one, and that one maxes out at like something around 40, okay, and that would be comparable to a slow wooden roller coaster. So even though the minimum speeds are about the same, when you start looking at the positions of the medians and the different quartiles, then you start seeing the discrepancy here, okay? You could even say Q1, the first quartile of the steel, it looks to be higher than the median of the wooden roller coasters. So whatever you want to say. So so don't just stop your explanation at steel is faster than wooden, but go into some of the details behind it, okay? But yes, overall the big picture is steel is faster than wooden, okay? And so we're just comparing some box plots here, okay? How are we doing on time? Okay, let's we'll go through. Okay, so I'm going to just so that will be it for chapter 5. You've got a few homework problems from chapter 4 and chapter 5 going into box plots and making some comparisons that way. And then, and so I'm going to get into Chapter 6. We'll just start talking about Chapter 6, and then we'll take a break, and then we'll finish off the rest of Chapter 6. Okay. So Chapter 6. This is okay, so Chapter 6 is the standard deviation as a ruler and the normal model. And we'll really get into the normal model quite a bit in this course. But before we get to the break, I'll only be able to talk about the standard deviation as a ruler. Okay, so for this example, or to get into this idea of the standard deviation as a ruler, if you had to take standardized exams, a lot of you probably took the SAT test, okay? And then and it would tell you, your score was 1100 or your score was whatever, 700 math or whatever, okay? Meanwhile, if you were out in the Midwest, you might have taken the ACT, all right? And if someone scores a 1500 on the SAT, which is like a good score, right? And then versus the ACT score of 21, how do you make these comparisons, okay? And so we're kind of trying to compare apples to oranges, and we need some way to standardize our scores here, okay? Or some way to put them on some sort of scale where the numbers, where we can compare these numbers, okay? And so that's where we're going to use the standard deviation, okay? So this example, I'm not even going to use SAT or ACT scores, but we're going to look at some Olympic results, okay? And this is the 2004 Olympics. Where were the 2004 Olympics? I can't even remember. Greece, Athens, yes. So, and we're looking at women's heptathlon. So how many events are in the women's heptathlon? Hept is one of those weird things. 7, yes. Seven events, okay, but we're only going to look at 2 of them. And we're going to look at the long jump and the shot put. Okay. All right. And the highest performing long jumper was Carolina Kluft. All right. She was the best performing long jumper, and she jumped 6.78 meters in the long jump, okay? And the highest performing shot putter was Austra Skuite of Lithuania. All right, and I don't know if I pronounced her name correctly or not, but we're just going to say her name is Skuite. And she threw her shot put 16.4 meters, okay? Kluft, she threw her shot put 14.77 meters. And Skuite jumped 6.30 meters in the long jump here, okay? All right. So if we said, we might ask, who was the overall, so Kluft had the longest long jump, and Skuite had the best shot put score, okay? But then we might ask, which score was more impressive? Was Kluft's 6.78 long jump score more impressive than Skuite's shot put score? Okay. And based on these numbers, we really can't know. Okay, we have to know the other people, the distribution of the other scores for us to even be able to begin to make a comparison. Okay, and if we wanted to say who is the overall better performer between the two competitions, we might be tempted just to add this. They're both in meters, so why not just add them across, and we'll get 20, 21 something over here and 20 something else over here. But we can't do that because the distance, 6.78 versus 6.30, maybe that's a huge performance difference, or maybe it's not. And maybe 16.40 and 14.77, maybe that's a huge performance difference, or maybe it's not. Okay, so I'm going to just start providing a little bit more information while also trying to keep track of our time. And we might have to take a break in the middle of this example. Maybe not. Okay, so the mean long jump score was 6.16 meters. And the mean shot put score was 13.29 meters. Okay, so both of these performers, okay, so Kluft had the best long jump, but Squite was also above average. Okay, and Squite had the best shot put, but Kluft was also above the average. Okay, the standard deviation here is 0.23 meters. Okay, and there were a total of 26 contestants in the long jump. And over here, the standard deviation is 1.24 meters. And there were a total of 28 contestants in the shot put here. Okay. And here I'm going to draw two stem and leaf plots for one for the long jump and one for the shot put. Okay, so long jump stem and leaf plot. Okay, so I'm going to start off with best. Okay, so when I have 67 bar 8, that corresponds to 6.78 meters. Okay. Okay, so over here we've got the long jump thing, all right, and so we can see Kluft's long jump score is this one right here, and Squite's long jump is this one right here, the 63.0, okay? And for the shot put, so forgive me, the best shot put was 16.4, and then excuse me, 59, 5923, okay, 1414. Okay, and so Squite's shot put score was the best, and Kluft's long jump score is 14.8, okay? So when we look at the stem and leaf plots, okay, we can see that the top performers are they're separated from the rest of the pack. Okay, so the rest of the pack is over here, and but the top performers are kind of separated from the rest. Okay, but who is kind of separated from the pack even more? Okay, and it might be a little bit difficult to tell, but this is where we can use the standard deviation as a way. Okay, and if you're busy copying all of these numbers down, don't worry about the exact numbers, but just get the overall. Again, remember the stem and leaf plot is kind of like a histogram, but we've broken out the actual numbers. So you just want to get the overall shape of this this thing. Okay, just get the overall shape of the histogram, so you know that this guy or Carolina Cleft was much higher than the rest, and Squite was much higher than the rest. Okay, so the exact values are not as important as the idea that our top performers have separated themselves from the rest of the pack. Okay, all right. So the way we're going to compare these numbers to the rest of the pack is we're going to use something called a z-score. Okay, and a z-score is the number of standard deviations a point is above or below the mean. Okay. All right. And the formula, the way we find the z-score is the z-score is equal to the point we're interested in minus the mean, all right, y bar, divided by the standard deviation s. Okay? All right. Now, forgive me for doing this, okay? But later on in the chapter, you will see also this equation, which is equivalent, but we throw in Greek letters, okay? And so I'm just going to show them both to you, so it's not like a shock or confusion later, okay? But we've got y minus mu divided by sigma, okay? But in both of these cases, y bar and mu, these are both symbols for the mean, and s and sigma are both symbols for the standard deviation, okay? So maybe I should write that up here, and I'll say mean, the symbol for mean is y bar or mu, okay? And the symbol for standard deviation is either s or sigma. Okay, but both of these, we've got y minus the mean, and that quantity divided by the standard deviation, okay? And over here we've got it with the Greek letters, and over here is the regular alphabet that we're used to, okay? Okay, so we can find the z-score for Cleft's long jump, and we can also find the z-score for Squite's shot put, okay? So for Cleft's long jump, her z-score, so this is for Cleft's long jump, her z-score is equal to 6.78, that's her y, okay, minus the mean is 6.16, and we're going to divide by the standard deviation of 0.23. So we do 6.78 minus 6.16, and we divide by 0.23, and we get the z-score is equal to 2.70. All All right, and if we do the same for Squite's shot put, we get her z-score is equal to z is y. Her shot put score is 16.40 minus the mean shot put score of 13.29 divided by the standard deviation of the shot put scores, which is 1.24. And when we do that, we get 2.51. Okay. All right. So this means Carolina Clough's, her long jump is 2.7 standard deviations higher than the mean. Squite's shot put score was 2.5 standard deviations higher than the mean. So they're both a couple standard deviations higher than the mean, but if we had to make a direct comparison, Clough's long jump score is more standard deviations away from the mean, so her long jump score is more impressive than Squite's shot put score, okay? They're both very impressive, okay? You can see that they both separated themselves from the rest of the pack, but Carolina Clough has more so separated herself from the pack, okay? Because her z-score is even higher than Squite's shot put score, okay? So with this small standard deviation, it just means the distance jumping 6.78, which is only, is like half a meter longer than the average, is a lot more difficult than throwing the shot put, 3 meters further than the average.
Is this what they use to judge the athlete's performance and overall winner of the heptathlon?
No, they don't. They don't use it.
That seems unfair. What if one group decides to focus on long jump? Then the shot put would be more impressive. And they'll have flimsy arms. Yeah,
and that's true. There's other races like in skiing, you've got like the alpine combined, and you've got like the slalom and the downhill and the things like that. They just add up the times, okay, directly. But it's a lot harder to shave off times off of the really fast one versus like the slalom, okay? And so if you just have a tiny bit of a bad run on the slalom, okay, and you add up extra time on that, it messes you up, okay? And it makes it that much harder to make it up on the downhill. And so certain things, they don't use the z-scores and stuff, but in terms of this, they don't use z-scores, but as a statistician, I think, I don't know, we probably favor using the z-scores here, okay? I will get into more of all of the standard deviation stuff, but do we have any questions regarding finding the z-score and what the meaning of a z-score is? It's the number of standard deviations above or below the mean, but I don't know if that has sunk into in terms of any tangible meaning for you guys yet. Yes, we have a question.
So z-score can be negative?
Yes, z-scores can be positive or negative. So in this case, both of our z-scores were positive because they both scored above the mean, okay? But if somebody scored below the mean, someone's below average, their z-score would be negative. Yes, z-scores can be positive or negative. Standard deviation is always positive, but z-scores positive or negative. Good question. Okay, if there are no further questions, why don't we take a short break. My clock says 8:31, so be back by 8:45, and we'll resume our exciting coverage of Chapter 6 here.